Good morning, students. Hi, Niharika. Happy birthday if it's your birthday. Yes, very, very good morning to all of you. So today's topic is going to be about reaction mechanism in organic chemistry. Reaction mechanism. In organic reactions or organic chemistry. Okay, up to last class, we have already discussed about Chandana Shri, very good morning. Jyothi Shri, Sai Swaroop, very, very good morning, everybody. So, in the last class, we have talked about isomerism. We have seen structural isomerism, we have seen geometrical as well as optical isomerism. Taking our train ahead to the next topic, which is going to be reaction mechanism. See, when you want to study organic chemistry for class 12th, this topic of class 11th must be on fingertips for you. Happy morning, Ratika. This particular topic must be on fingertips for you. If you know this topic, trust me, when a reaction is written next to you, most probably you can get the right answer yourself as well. Okay, if you know the topic reaction mechanism, many times you might have not seen the reaction, but you can easily think what will happen, what product will form. Okay, so this is a very important, it's very basic, very simple, but very important topic, that whenever any aldehyde is given, you will automatically think aldehyde is there, nucleophile is there, I should do nucleophilic addition reaction. Whenever any haloalkane is there, you will think haloalkane is there, nucleophile is there, I should do nucleophilic substitution, not addition. Whenever alkene is there, you will automatically think alkene means electrophilic addition only, no other addition reaction. Like that, by knowing the name of the chapter, you can easily learn what type of, or you can easily understand what type of reactions will they undergo. Okay, whenever you see a aldehyde and you see a base is coming to it, aldehyde base, you will think aldehyde will do their reaction due to acidic proton, which is aldol condensation, like that. So simply by knowing simple reaction mechanisms, you can predict so many reactions, and then learning organic chemistry becomes very, very simple. You don't have to mug up anything. Okay, so let us start reaction mechanism. See, whenever reaction happens, the species which is reacting is called as a substrate, you can call it. The reactant which is reacting, we call it as substrate. Okay, this substrate can be a alkane, alkene, alkyne. This substrate can be a haloalkane. It can be a alcohol, phenol ether. On substrate, a attacking species comes and attack. All of you know this. Attacking species comes to attack. Okay. When the attacking species attacks on the substrate, some old bonds of the substrate will break. And after breaking the old bonds, there is a possibility that a reaction intermediate will form. Reaction intermediate will form. Reaction intermediate is a kind of an unstable state, kind of an unstable, intermediate, which is not your final product, but it is an electron deficient or electron rich species, something like a carbocation, something like a carboanion, or a free radical. Three types of intermediate we will study. Others are also there, like carbene, benzene, nitrene. So this is what is reaction intermediate. This is not the final product. Intermediate means in between the reaction it is formed. Then what will happen? Some new bonds will form and you will get your product. Okay. So when I start with a alkene, if I want to go to a alkane, or if I start with a alkene, let's say, if I start with a alkene, if I want to go to a haloalkane, something like this. If I start with an alkene like propene, if I start with a propene and I want to go to 2-bromopropane, let's say, this is the reaction that we are talking about here. So product is 2-bromopropane and substrate is propene. Here in between an intermediate will form that you will study in the next chapter, which is in the Markovnikov addition. Intermediate is this carbocation. Okay, and attacking species here will be a H positive coming from HBr. Okay, so this is going to be attacking species. So it is going to be called as a electrophilic addition reaction, because overall what is happening here? Here a addition is happening. There was a pi bond. In that pi bond, HBr is added. HBr is added. Actually, H plus adds first. And then finally Br minus comes and adds here like this. Okay, we will see the bonds and how to move the bonds and everything, how electrons will move and bonds will form. We'll do that when the reaction mechanism will start. Right now, I'm just telling you definitions. Okay, so when there is a substrate, means the reactant, attacking species will come and attack on it. In this case, attacking species is electron loving species. We call it electrophile. Electrophile adds first, then a nucleophile comes and adds. So this is known as a electrophilic addition reaction. Like that, total 7 to 8 type of reactions will come. Electrophilic addition, nucleophilic addition. So as soon as we look at the substrate, we would be able to think that what type of reaction it will undergo. And if any attacking species is given, you can easily predict the product, whether it will be a Markovnikov addition, anti-Markovnikov addition, or what. So we'll talk about these things. First, let us talk about substrate. So among substrate, we should know that how the bond breakage takes place in substrate. Okay, so first thing we are talking about substrate, which is any carbon compound, any organic compound. So number one, you can say bond cleavage in substrate. Bond cleavage in substrate. So beta, a bond between two atoms can cleave by two methods. Okay, by two methods, homolytic method and heterolytic method. Homo and hetero. If the question is in how many ways a bond can be broken, how many ways a bond between two atoms can be broken, answer is 3 ways. Answer is 3 ways. One is homolytic way, which is equal distribution of electron after breaking the bond. And there are 2 homolytic ways. There are 2 heterolytic ways. In the heterolytic way, A can take both the electrons or B can take both the electrons. So how many methods to split a bond? 2 methods. Homo, hetero. How many ways a bond can be split? 3 ways. Homo, 1 option. Let's say myself and you, we are making a bond with one electron. Homo means 1 electron I will take after breaking the bond. 1 electron you will take after breaking the bond. This is homo. Hetero can be of 2 types. I take both the electrons, I become negatively charged, you become positively charged. Or you take both the electrons, you become negatively charged and I become positively charged. So 3 ways. Okay. So please remember it. There are 3 ways in which a bond can be cleaved. There are 3 ways to break a bond between 2 atoms. Okay, one way is homolytic, one way, and other is heterolytic, where there are 2 ways of heterolytic. Okay, so for example, if I take a carbon which is attached to some groups, I don't know which groups these are. First, I am showing you homolytic cleavage. Then I will show you heterolytic cleavage. So what we will do here is, we will draw it as a differentiating table. Okay, this side homolytic, this side heterolytic. Okay, so let's say carbon is attached to some group. I'm calling the group to be G group. This may be a hydrogen, this may be a carbon itself. So carbon-carbon free radical cleavage happens, but it is very rare. Sometimes with hydrogen this cleavage happens in the free radical reactions. So free radical substitution reaction you will study in the alkane chapter. So whenever this bond cleaves homolytically, homolytic means equal split. So this bond was made up of 2 electrons. We say carbon, you keep 1, G, you keep 1. So whenever you make movement of 1 electron, always show it by fish head arrow like this. Okay, this is a complete arrow. Whenever 2 electrons move, you show complete arrow. Whenever 1 electron move, you show half arrow or fish head arrow. Okay, so cleavage will happen. Keep it as a point that whenever you are doing a homolytic cleavage, always sunlight or heat will be mentioned. Okay, sunlight h nu, E equal to h nu. Okay, Planck's quantum theory. So some energy will be required to do homolytic cleavage. Okay, so let it be. Homolytic cleavage will require some sunlight or heat. Okay, so when this will happen, you are finally going to get a free radical of carbon and a free radical of G. This is known as free radical. Free radicals are what? They are odd electron species, but they are neutral. They are odd electron species, but they are neutral. Okay, so this is our carbon free radical. I have drawn it like this because carbon free radical actually has a sp2 hybridization and it is planar in nature. So you can also keep it like this. Carbon with 3 bonds and the p orbital of carbon will carry 1 unpaired electron like this. Okay, this is carbon free radical. It is one of the reaction intermediate, what is formed here. So after breaking the bonds, whatever carbon moiety is remaining, whatever the part of carbon is remaining, that is known as an intermediate. So this is carbon free radical. Okay. Now let us do heterolytic cleavage. Now it is possible that carbon is attached to a more electronegative atom like chlorine, bromine, iodine. Let me keep chlorine here. Okay. Or it is also possible that carbon is attached to a electropositive atom like magnesium in the case of Grignard reagent. Possible. Sometimes carbon can be attached to halogen. Sometimes carbon can be attached to a metal like magnesium, lithium, and so on. This is called as a Grignard reagent. Now what will happen? If homolytic cleavage was happening, equal bond was getting shifted. Here both the electrons, more electronegative atom, chlorine will take away. So what will happen? After some time, an intermediate will form where carbon has 3 sigma bonds and a positive charge. So carbon has lost its shared electron. Carbon becomes positive, chlorine becomes negative. Chlorine becomes negative. So homolytic cleavage give rise to neutral molecules, and whereas the heterolytic cleavage gives rise to charged ions. Charged ions. If you get a cation, we'll call it as carbocation. Carbocation. Other name of this cation is carbonium ion. Carbonium ion. Okay. Remember it. Carbonium. Ium means a cation. Magnesium, sodium, aluminium. So wherever Em is there at the end, it is always a cation. Carbonium ion. Whereas in the other case, if magnesium is attached to carbon, then carbon is more electronegative than magnesium. Carbon will say, I will take both the electrons. So carbon will get a lone pair. 3 sigma bonds and a lone pair. Carbon will become sp3 hybridized. So it will be pyramidal in shape. It will be pyramidal in shape. So 3 shapes I have just told you. Beta, carbocation is trigonal planar. Free radical is trigonal planar. In carbocation, the p orbital is vacant. Nothing is there in that. In the free radical, there is 1 electron in the p orbital. And whereas in the carb anion, we call it carb anion. In carb anion, there is no p orbital present. Okay. These are all sp3, sp3, sp3 hybridized orbital. 3 of the sp3 orbitals are making sigma bonds. 1 of the sp3 orbital is keeping a lone pair. This is carb anion. Carb anion. MgCl positive goes out. So these are the ones. Sir, conversion of cyclohexene to cyclohexanol can be conveniently achieved by add water into it, beta. Add water into it. Acidic hydration we call it. Okay, next one. So let us write down about differences between homolytic versus heterolytic cleavage. Homolytic versus heterolytic cleavage. First point is it produces neutral radicals which are paramagnetic in nature. Paramagnetic because they are odd electron species. Okay, paramagnetic because they are odd electron species. Both will carry one unpaired electron. Heterolytic, on the other hand, it will produce ions, positive and negative charged ions. Positive and negative charged ions. So next point. Always remember that homolytic cleavage generally requires sunlight or a peroxide as initiator. Requires initiators. Initiators are those which help the reaction to proceed. To help free radical reaction to proceed, homolytic cleavage to proceed, you either require sunlight or you can take high heat or you can take a peroxide. Okay, peroxide. Any peroxide compound you can take. H2O2 you can take. Okay, you can take benzoyl peroxide and so on. Whereas heterolytic does not require any initiator. Just water. Do any reaction inside the water. I mean, these type of reactions are very easy to do inside the water because water has very high dielectric constant. Water loves to split ions. Like when you put NaCl into water, water splits it into Na positive and Cl negative. So like that. So next one is about solvent. So mostly homolytic cleavage will not take place inside water. Water is a very polar solvent. Okay, polar solvent means it likes charges. So water likes to bring charges to people. It will do heterolytic because here charges are there. Homolytic will take place in non-polar solvents like benzene, or they may take place in gaseous state only without a solvent. Okay, so this one takes place in non-polar solvents or gaseous state. So if you look at the example of free radical substitution of alkanes, it will take place in gaseous state. Whereas heterolytic takes place in polar solvent. Takes place in polar solvent. Okay, sometimes non-polar solvents can also be taken here, but majorly achieved in polar solvents like water, alcohol, carboxylic acid, etc. You can take liquid ammonia as well. In liquid ammonia also it can take place. So these are the important points. Then one more point that you should remember is heterolytic has more bond dissociation energy. Means if you want to break the bond of heterolytic cleavage, because there is a separation of too much of electrons, it requires much more energy as compared to homolytic. So homolytic requires, so this has less bond dissociation energy. This one has more bond dissociation energy. Okay, I hope these points are clear to you. I hope that these points are clear to you. Less bond dissociation energy and more bond dissociation energy. But whenever we talk about bond dissociation energy, no, one thing is fixed. You must break the bonds in gaseous state. Okay, you are not allowed to take water. If you take water, this reaction becomes very easy to do. So whenever you are comparing two people, always compare them in same grounds. So whenever we talk about bond dissociation energy, when you study its definition in your thermodynamics chapter, you will study that bond dissociation energy is the amount of energy required to break any bond in gaseous state. To break any bond in gaseous state. So here bond dissociation energy, we mean to say if AB gas breaks into A radical gas plus B radical gas, if this is delta H1, let's say, and here same AB gas breaks into A positive gas and B negative gas, and let me call it as delta H2, then delta H2 is greater than delta H1. Delta H2 is greater than delta H1. Delta H2 much greater than delta H1. Okay, so this is the thing about the two types of bond cleavage. Okay, now bond cleavage has happened, let's say. When will bond cleavage take place? Automatically, if I keep some alcohol in this room, obviously there is no bond cleavage that is going to happen. Okay, if I keep some alcohol will remain alcohol only. If I keep some alkyl halide, it will remain alkyl halide. Why will the bond break? Bond breakage takes place when a attacker comes. When a attacker comes. What is the attacker called as? Attacker is called as attacking species. So let us talk about attacking species now. So second thing after substrate, we have attacking reagent or species. Both mean the same thing. Attacking reagent. Okay. Who is the attacking reagent now? Attacking reagent can be an electron rich or deficient person who comes and attacks on substrate. Electron rich or deficient species which attacks on substrate in any reaction. In any reaction, any electron rich person or electron poor person who comes and attacks is called as an attacker. Now they are of three types. We call it as electrophile, means electron loving. So they are electron deficient species. We'll show them as E positive. They may not be positively charged always, but electrophile generally represented as E positive, electron loving nature. Then is nucleus loving, nucleophile. Who will love a nucleus? Nucleus is positively charged. So a electron dense person, electron rich person will love a nucleus. So I'll show it as Nu negative. It is not always that nucleophiles are negative. Nucleophiles can be neutral as well sometimes. And then we have free radicals. Okay, free radicals are those which carry single electron. We'll call them as radical. R dot I'm writing. Free radicals. Three types. Okay. Now, if in the rate determining step, if electrophile comes and attacks, we call it as electrophilic reaction. Maybe electrophilic addition, maybe electrophilic substitution. When a nucleophile comes and attack in the rate determining step, we call it nucleophilic reaction. Maybe nucleophilic addition, maybe nucleophilic substitution. Same way, free radical addition, free radical substitution. 6 reactions are there which you have to remember. Okay, all of them examples I'll be giving you in the next class. This is just the basics of mechanism class. So let us see the examples of electrophile. Let us see the examples of nucleophile. Okay, free radicals are very rare and very few only. So you can leave the free radical, only will write the examples of nucleophiles and electrophiles, and see carefully where you will do mistake. Okay, mostly you will do mistake in the neutral species. You will give the answer wrong. So see here, electrophile beta, electron deficient. First of all, most of the cations are electrophiles. Most of the cations, except few. Something like ammonium NH4 plus is not an electrophile. Okay, NH4 plus में nitrogen already has 4 bonds. So nitrogen is electron rich only. Hydrogen also has complete bonds. So few cations are not electrophile, but most of the cations are electrophiles. Most of the cations I am saying. Okay. So examples. Cations. You can write the example of cations. Any cation you mention, Mg plus 2. Obviously, to become magnesium, it needs to gain 2 electrons, so it is electron deficient. Na positive. Okay. H positive. NO2 positive. Now, whenever you think of electrophile, remember there are 5 major electrophilic reactions which happen in benzene chapter. We call it electrophilic substitution reaction, ESR. They are nitration, where NO2 plus takes place. Halogenation, where Cl plus Br plus react. Nitration, halogenation. Third one, Friedel-Crafts alkylation, where carbocations will react. So carbocation, CH3 positive, CH3, CH2 positive. Then comes Friedel-Crafts acylation. Acylation में RCO positive reacts. This is a acyl carbocation, acyl. Okay. Then we have sulfonation, but sulfonation may SO3 is the electrophile. It's not a cation. Okay. So these are few of the examples you should remember. H plus will take place. We'll see many examples in the alkene chapter. That in alkenes, when you do addition of HBr, H plus is the attacking species there. Okay. These are the examples of cation. What are not electrophiles? You should remember. Nitrogen making 4 bonds. It is not an electrophile. Nitrogen making 4 bonds. It is not an electrophile. Oxygen making 3 bonds. It will have a positive charge, H3O positive. But these are not electrophiles. Remember it. So oxygen making 3 bonds will get a positive charge, but it will confuse you. It is not electron deficient. Okay. Nitrogen making 4 bonds is not electron deficient. This is something we should remember. Okay. NH4 positive, H3O positive. Okay. These are not going to be electrophiles. Then comes neutral electrophiles. Now, a neutral electrophile may be of many types. Here you should remember the example of Lewis acids. Lewis acids, those who have an empty p orbital or empty d orbital. Who has an empty p orbital? Empty p orbital is available in boron compounds. Boron making 3 bonds. BF3, BCl3, B2H6, H3BO3. Okay. Aluminium compounds making 3 bonds. AlCl3. Okay. AlBr3, AlI3, these ones. AlF3 is not. AlF3 is an ionic compound. So AlF3 cannot be put here as an exception. You can remember if you want. AlF3 is not a electrophile. So AlF3, don't put it. Okay, cut it. AlF3 is actually a ionic compound, just like NaCl. It's a salt only. Al plus 3, F minus 1. All of them are electron, all of them are electron precise. So this is not an example of electrophile. So these are the examples of neutral ones. Who else? Then you can think of any compound where the central atom belongs to third period. Central atom belongs to third period. Third period, fourth period, fifth period, they will have empty d orbitals. FeCl3, FeBr3, FeCl3, FeBr3, SnCl4, etc. They have empty d orbital. They have empty d orbital. So they can also act as electron acceptors. Then who else? Then comes the last ones, wherever you see a double bond or triple bond with oxygen, okay, like CO2, like SO3, like SO2, etc. They can also act as electrophile, like in sulfonation reaction, SO3 is very important example, SO3. In Kolb's carboxylation reaction, CO2 is also an important example. Kolb's carboxylation you might have seen. When you take benzene, when you take phenol, and you try to convert phenol into salicylic acid, then CO2 is used as an attacker. These are the examples, very, very important ones. Electrophiles. These people will always and always and always react with alkenes, alkynes, and benzenes. Alkenes, alkynes, and benzenes. Alkenes are electron-rich species. They will attack on them. I mean, these people will attack on alkenes or alkynes or on benzene rings. So whenever anything happens on benzene ring, one of them will be reacting. So most of the reaction on benzene rings will be going on with SO3, sulfonation, Kolb's carboxylation, acylation, alkylation, halogenation, nitration. These are the ones. These are the ones. Then some of the neutral ones can be double radicals, which is like carbene, CCl2 carbene you can mention. This will be present in Riemer-Tiemann reaction. Have you heard of Riemer-Tiemann reaction? Anybody? Where dichlorocarbene will be electrophile. So whichever reaction will take place on that benzene ring of any organic compound, it is going to be this reaction, electrophilic substitution reaction. Riemer-Tiemann, halogenation, nitration, Friedel-Crafts alkylation, Friedel-Crafts acylation, Kolb's carboxylation. So many are there. Sulfonation. Okay. So remember them. These are the examples of electrophiles required for your level. There may be many more. No electrophile is negatively charged. Electrophiles are always positive or sometimes neutral. Now let us move on to nucleophiles, which are nucleus seeking. Nucleus seeking means positive charge seeking. So they themselves are electron rich people. Electron rich people. These are the ones who carry a lone pair. Now who carries a lone pair, beta? Every anion carries a lone pair, almost every anion. So we'll make the examples like anions. Anions. Best examples of anions which carry lone pair, all anions you can take. H minus. Few are not, like BF4 minus and all, but rest every anion you can take here. Okay. H minus. Then you can take a Cl minus, Br minus, I minus, F minus. You use Schwartz reaction where you use F minus as the attacker. You use Finkelstein reaction where you use I minus as the attacker. You use LiAlH4 from where H minus comes and attacks. Okay. Other anions you can take like CH3CO minus, you can do acylation reaction. So CH3CO minus can also act in the carboxylation reaction. There is one reaction in the alkyl halide chapter you will study. Cn minus, whenever you want to replace Cl with Cn, you use KCN, then Cn minus. NO2 minus, whenever you want to convert your alkyl halides to nitro compounds, you use AgNO2, KNO2, NO2 negative. Okay, these are the most common examples. OH minus, if you want to convert any alkyl halide to alcohol, aqueous KOH you use. Then you do Williamson ether synthesis where you use alkoxide, RO minus. You can take phenoxide, benzene O minus. Okay. Then other anions like NH2, amide, NH2 minus, amide. Okay. So many can be there. I have just written a very, very few examples which are here next to you. You can take SH minus if you want to make thioalcohol. Okay. So these are the ones, and then I'm writing etc. Okay. Where do you see nucleophiles? Beta, remember it. Please remember it. Nucleophiles you always will see in alkyl halide chapter, alcohol chapter, aldehyde ketone chapter. These three chapters. Alkyl halides will always undergo nucleophilic substitution, SN1, SN2. So you can replace a Cl minus with F minus, Schwartz reaction, I minus, Finkelstein reaction. You can replace it with Cn negative, NO2 negative, OH negative, OR negative, Williamson ether synthesis. NH2 negative, you can replace it with SH negative. These all you will find in these chapters. Then aldehyde ketones chapter, like CH3 minus. When Grignard reacts with aldehyde and ketones to give alcohol, then CH3 minus comes and attacks on aldehyde ketones. OH minus comes and attacks on aldehyde ketones. Okay, OR minus comes and attacks on aldehyde ketones to give you hemiacetal, acetal, and so on. Okay, so nucleophiles you majorly see in aldehyde ketones and alkyl halide chapters. Electrophiles, where do you see? In alkenes chapter, alkynes chapter, and in benzene ring chapter. Wherever benzene ring is there. In phenols you will study this because phenol contains a benzene ring. In nitrobenzene you will study them. So wherever benzene ring is there, always these things will be reacting species. Whenever haloalkane is there, whenever aldehyde ketones are there, whenever alcohols are there, then these people will react. Okay. Then other nucleophiles can be neutral nucleophiles. Now, who are neutral nucleophiles? Majorly neutral nucleophiles are beta oxygen and nitrogen containing neutral compounds. Okay, nitrogen making 3 bonds. Ammonia, best example. Secondary amine, primary amine. Okay, in all these cases, nitrogen contains a lone pair. Again, in the haloalkane chapter, ammonia can react, ammonolysis reaction. RNH2 can react. You will see this in the amines chapter when you do reaction of alkyl halides with RNH2. Okay, these are nucleophiles only. Then oxygen containing nucleophiles like water. Okay, oxygen containing nucleophile like alcohol. So ROH. These are neutral nucleophiles. Okay, most common nucleophiles are these. I hope it is clear to everyone. Now, there are few people who can act as nucleophile also, electrophile also. Means they carry electron rich center also, electron deficient center also. We call them as MB files. MB means dual character. MB means dual character. So MB files are those which can act as both nucleophiles as well as electrophiles. 2-3 examples we learn for them. There are other neutral nucleophiles also, beta. You can take alkenes, you can take alkynes, you can take benzene. They are also nucleophiles only, na? Neutral species who are electron rich, they are pi electrons rich. So they can come and attack on these people. This alkene can come and attack on H+. This alkyne can come and attack on H+. This benzene can come and attack on NO2+. So obviously one is rich, one has to be poor. So when two people are reacting, if substrate is rich, your attacking species will be poor. If substrate is poor, species will be rich. For example, if substrate is alkene, alkene is a rich person, then attacking reagent will be H positive. Correct? This is how we can remember. Many examples I'll give you, but keep remembering what I'm saying. Okay, it is very important. These are the examples I hope you have written for the nucleophiles and electrophiles. Last thing is, what is MB file? MB files are those which contain a electron rich center as well as electron deficient center. Okay. Now these are the people where a electrophile comes, then also they can attack on electrophile. If a nucleophile comes, they will be attacked by nucleophile also. So they can be attacked by electrophile also, they can be attacked by nucleophile also. For example, the best example of this is carbonyl compounds, means aldehyde ketones. This is how a ketone looks like. Beta, in a ketone, this oxygen is a rich person. He has a lone pair. And I told you that whenever there is a C double bond O, S double bond O, then those can also act as electrophiles. So here this carbon actually carries a partial positive charge. Oxygen carries a partial negative charge. Due to this polarity, this bond can easily shift here, beta. This bond can easily shift here. Pi electrons are very mobile. They keep moving. So if this bond shifts here, after some time, it will start looking like this. This compound will start looking like this, O negative, C positive. That means in this ketone, always there is some positive carbon present. So if any nucleophile wants to come and attack, it can attack here. If any electrophile wants to come, then O can attack on electrophile. Beta, one thing you should remember, always show the arrow from a rich person to a poor person. Arrow you will always show from a rich person to a poor person. Poor person will have some orbital, rich person will have some electrons. Arrow always show from rich to poor. So never ever say that electrophile comes and attacks. Beta, electrophile cannot attack. Never say that electrophile comes and attacks here like this. It is not possible. By arrow, we want to show movement of electrons. By arrow, we want to show movement of electrons. So actually, electrons are present on oxygen here, na? So oxygen will come and attack on electrophile. So when attacking species electrophile, substrate will attack on the electrophile. When attacking species nucleophile, nucleophile will attack on substrate. Okay, good morning Dinesh, very good morning beta. So these are called as MB files. These are called as MB files. So other examples also you can remember. Other examples of MB files are nitriles, aldehydes, ketones. Okay. RNO2 also you can take because there also double bond is present, etc. So whenever you see a double bond B kind of molecule, A double bond B kind of molecule, N double bond O, C double bond O, S double bond O, they are actually MB files. Here nitrogen is partial positive, oxygen is partial negative. So on nitrogen a nucleophile can attack, on oxygen a electrophile can attack. Partial positive, partial negative, partial positive, partial negative, partial positive carbon, partial negative nitrogen. I hope it is clear to everybody. If it is clear, you can mention a clear in the chat box. You can like the video if you are liking the class till now. Then we'll move forward to the reaction intermediates. Beta, I am Dinesh Rawat. I am from Haryana. Looking at your surname, I think you are also somewhere from Haryana or Rajasthan. Dinesh, because Rawat mostly are in Haryana, Rajasthan, no? Rawat or UP maybe. Where are you from, Dinesh? So, I hope this part is clear. Now let us go to the next topic, which is going to be reaction intermediates. Reaction intermediate. Uttarakhand. Okay. Yeah, Rawat are from Uttarakhand as well. Yes. So, reaction intermediates, let us talk about them. These are some unstable species unstable, charged or neutral species, unstable, charged or neutral species which gets formed during the course of reaction. A reaction intermediate can be isolated, but at a very, very low temperature. Okay. It's not like a product that you can keep it at room temperature and all, but you can isolate reaction intermediate at very, very low temperatures. There is another term called as transition state beta. They are very different from each other. Reaction intermediate is actually a real thing. It exists in reality. Transition state is an imaginary thing. Okay, it just comes from a particular theory called as collision theory. So where you have written the reaction mechanism here, whenever you draw an arrow, on the arrow you can also mention transition state 1 like this and show it as this sign. Okay, this represents transition state, and transition state 2, show this sign on the top. This sign represents transition state, and a transition state is just the imaginary state where we imagine that an attacking species coming to attack and another group is going out. We'll show how the transition state looks like in a particular reaction, but they are imaginary. We are imagining what is happening. But so transition state is an imaginary thing, but reaction intermediate is a real molecule. Okay, it's a real molecular cation. So these are the species which are getting formed during the course of a reaction. Examples of reaction intermediates are, 3 of them are important. Carbocation, where carbon will make 3 bonds and gets a plus charge. Carbanion, carbon makes 3 bonds, a lone pair gets a negative charge. Always show it as pyramidal shape and carbocation as a trigonal planar shape. And then we have radical, carbon free radical, where carbon makes 3 sigma bonds and keeps 1 lone pair, 1 unpaired electron. Then we have something called as a carbene beta. A carbene is formed when you do 2 homolytic cleavage in a compound. So carbon was having 4 bonds, let's say 1, 2, 3, 4. If you do 2 homolytic cleavage, let's do homolytic cleavage here also, here also. So you'll get 1 radical here, 1 radical here. This is carbene. A carbon with 2 unpaired electrons. So carbene contains 2 bonds. Carbene contains 2 bonds and 2 electrons, like this, like CCl2 carbene. Like CCl2 carbene. This is carbene, not very important. Others are also there like nitrene, but you can learn one more, benzene. Benzene comes from benzene plus ine. Ine means alkyne. This is how benzene looks like. Benzene having a formula of C6H4, it's not a real compound. I mean, it's not a product or a reactant. Okay, it's very unstable. It only exists at very low temperature, so we call it as an intermediate only. Benzene is a real organic compound. Benzene is not a compound. Benzene is just an intermediate. Okay, etc. Others can also be there, but these are the ones important for us. Now, as a differentiation between carbocation, carbanion and free radical, 5 points to remember about them. 5 points about carbocation, 5 points about carbanion, 5 points about carbon free radical. 5 points about all 3 of them we are going to learn. Okay, it's time for that now. So let us start. Write down carbocation, carbanion and free radical. Carbocation, carbanion and free radical. For each one of them, few properties we are going to study. All right. What is the first property we should know? First property, let us know about their nature. Let us know about their nature. Carbocation is electron deficient. As the name suggests, it's a cation. This is electron rich. This is also electron deficient. Okay. Radical is also electron deficient in nature. So if we look at a radical, in carbon radical, there are 3 bonds and 1 single electron. So total 7 electrons are there in the octet. So why are we saying deficient and rich? Look at their octet. Carbocation has incomplete octet. Means only 6 electrons are there in the valence shell of carbon. So it has carbon with 3 bonds and a positive charge. So 6 electrons in the octet. 6 electrons in octet. Octet means valence shell we are talking about. 6 electrons in the valence shell of carbon here. So this carries a empty p orbital. So it is electron deficient in nature. Vacant p orbital is present. Vacant p orbital is present. Free radical also is having incomplete octet beta. Here it has 7 electrons in its octet. Same as a carbocation, just that the p orbital is not completely vacant, but it is half filled. Like this. 7 electrons in octet. Octet means valence shell. It's actually wrong to write octet. Octet means 8. Here we are trying to say 7 electrons in the valence shell of carbon. 8 were required to complete the octet. Electron rich person is carbon ion, but it has a complete octet. Okay. Electron rich does not mean expanded octet. Okay. Electron rich just means that it carries a lone pair. So this is how a carbon ion looks like. A carbon with a lone pair and 3 sigma bonds. So we know whenever we want to find the hybridization, we count the number of sigma bonds plus lone pair. Sigma plus LP. Sigma plus LP is 3 here. 3 represents sp2 hybridization. So next point we'll write about hybridization. Next thing we'll talk about shape. Okay. So it is sp2 hybridization and its shape is trigonal planar. Trigonal planar. Here sigma plus lone pair are 4. 3 sigma, 1 lone pair. 4 means sp3 hybridization. sp3 means it will become a tetrahedral shape or a pyramidal structure. I hope all of you know what I am talking about. I will not explain it here. So it has a pyramidal shape. So its shape is pyramidal. Whereas again this one is sp2 because 3 sigma bonds and no lone pair. So here also steric number is 3, sp2, and it is also trigonal planar. With one exception, remember it, one exception is there in the radical. The exception is CF3 radical. Only there is one radical which is actually pyramidal in shape, which is CF3 radical. So as an exception, on the next page you can write if you want. On the next page you can write if you want. I am just writing it here. Exception. CF3 radical. And one more radical is there, which is bridgehead radical. I showed you what is bridgehead carbon in the tautomerism. So CF3 radical and bridgehead radical. If a radical is there on the bridgehead carbon like this, these two radicals are pyramidal in shape. Completely an exception that you need to remember. Okay. These radicals are found in means during the reactions, and these radicals were not found to be planar, but they were found to be pyramidal, just like a carbon ion. Okay, rest are trigonal planar. Carbocations are always trigonal planar without any exception. Without any exception. Okay, so shape is done, hybridization is done, shape is done, hybridization is done. Exception is done, nature is done. Okay, what else should we know? We should know about now how do they act as. Okay, how do they act as? So next point you can write acts as. Beta, carbocation will act as an electrophile, obviously. It is electron deficient person. This will act as a nucleophile. Carbon ion will act as a nucleophile. And radicals are not electrophiles, remember it. Radicals are electron deficient, beta. But electrophiles are those which gain a pair of electrons. Electrophile to already, your carbon radical to already has 7 electrons. How it will gain 2? It can't gain 2. Radicals are radicals only. So they act as radicals. So there are 3 types of attacking species I told you. Electron rich, electron deficient, and radicals. Radicals are themselves a new type of, a different type of attacking species. I hope it is clear to everyone till here, yes or no? Is it clear to everyone? So carbocations are electron deficient and electrophiles. Radicals are electron deficient, but they are not electrophiles. They don't want to gain 2 electrons. They can't gain 2 electrons. And the last point that we can mention is factors affecting stability. This is the very, very important point. It will be studied in the next class under the electronic effects. The electron migration effects we'll study in the next class, where you will talk about inductive effect, mesomeric effect, and hyperconjugation effect. So those are the factors which will stabilize them. So next point you can write down stability. Stability. But carbocations are electron deficient. So obviously, if you want to stabilize a carbocation, you supply electron. So for them, stability is directly proportional to electron donating groups. They are very happy if they are attached to electron donating group. EDG means electron donating groups. We call them as plus M, plus I, plus H groups. EDG means plus M, plus H, plus I groups. In the next class, I'll show you. And stability is inversely proportional to electron withdrawing group. Those who pull the electron, EWG, we call them as minus I, minus M, minus H. So electron withdrawing groups destabilize them. Electron withdrawing groups destabilize them. Plus I, plus M, plus H makes them happy. Minus I, minus M, minus H makes them unstable. Same for the radical, because radicals are also electron deficient, beta. Same for the radical. Opposite for the carbon ion. Carbon ion already carry a negative charge. Carbon ion already carry a negative charge. So these are negatively charged species. If you start supplying electron, they'll become more negative. They'll become very, very unstable. Nobody wants to remain charged. Charge always brings destability. Okay, neutral things are always stable. So when you want to neutralize this person, you should pull electron from it. So here stability is directly proportional to electron withdrawing groups. Electron withdrawing groups will make it happy, which is -m, -I, and -H. Whereas stability is inversely proportional to electron donating groups, which is +m, +I, +H. +m, +I, +H. They will make it sad. The best example of electron donating groups are alkyl groups. Alkyl groups, as an example, all of you know they are +I. So more alkyl groups attached to carbocation are good. That's a good thing. That's why when you look at a tertiary carbocation, it is a much better carbocation than a primary. Tertiary carbocation will look like this. A carbon attached to alkyl groups on all sides, tertiary carbocation. And the alkyl group is electron donating group. So when it is attached to electron donating group on 3 sides, it is very, very happy. When it is attached to only 2 electron donating groups, then it is not that happy. When it is attached to only 1 electron donating group, then that is not at all good carbocation. So carbocations are always stable when they are attached to so many alkyl groups. So tertiary carbocation is very, very happy as compared to a secondary carbocation, and a primary carbocation is not at all good. Okay, so this is the major example that every time gets asked in small exams, also in NEET sometimes. Okay, I hope this stability order, all of you remember it and I don't have to explain it. Is this clear, yes or no? In the case of radical also, same thing. When you have a radical which is tertiary, a tertiary radical is a very happy radical. So instead of a plus, I can put a dot here. Instead of plus, I can put a dot here. Do we know this? Yes or no? If you know about this, just say I know in the chat box. And for carbon ion, it will be opposite because carbon ions are destabilized by donating groups like alkyls. Opposite will happen. Opposite will happen. So carbon ion tertiary is very happy. Secondary, okay. Tertiary is very, very sad. Primary is very, very happy. So most happiest carbon ion is primary because it is already negative charge and one person is donating here. It is already negative charge, 2 people are donating. It is already negative, 3 people are donating. It will become very, very unstable. Okay, so we'll keep our class up to here. Quickly write it down. I'll keep this, meeting open for next around 10 minutes so that you can note down everything. Once you have noted it down, then you can leave the class by liking the lecture first. Okay, like this video. See you all in the next class. Bye bye. Thank you for coming, everybody. See you all very, very soon. When are you going to join the campus? And where are you going to join? Can you tell me? Which campus are you planning to join? Niharika, Chandana. Which campus are you planning to join? And when are you planning to join? I'll wait for your reply. Offline from tomorrow. Where will you be coming, Niharika? Which city? Hyderabad. Okay. DSNR. All right. Good. What about Chandana? What about Dinesh Rawat? Okay, you don't know, your father will decide. All right. Okay. All right, everybody. Bye bye. Take care. See you all in the next class.